Not yet, I don't think.
Uh, our presentation is on the happiness. The next.
I'm Chloe.
I'm Michelle.
I'm Toma.
Next slide.
Our model is trying to explain happiness based on various factors such as GDP per capita, average income, and life expectancy of different countries and societies.
Next.
We have a lot of independent variables, but first let's start off with our dependent variable, or what we're trying to calculate, which is our ladder score. It's essentially our happiness score and how happy they are. It goes from 1 to 10. Basically, you imagine there's a ladder with 10 steps. If you're on the 10th step, you're very happy. But if you're on the first step, you're kind of sad, like you're depressed. Our independent variables are pretty simple. GDP per capita, gross domestic product per area, in a certain amount of time. Basically, usually when a society has more products and they produce it more often, they tend to have a higher quality in life, and that tends to make people happy when you have a higher quality in life. Healthy life expectancy, basically how long you live according to statistics and data. If you have a longer life, you have more time for fulfillment, and usually, again, that makes a lot of people happy when you can spend time with family, go traveling, etc. The Human Development Index is essentially the quality of life. Basically, when you have a higher quality of life like before, it tends to make people pretty happy. Social support, I don't think I need to explain why this makes people happy. It's just support you get from your friends, family, etc. Just support in general. Freedom of making life choices, again, something really simple to understand. Basically, just how much control you have over your own actions. Usually, when you have more control, you tend to be happier with your life because you can make choices. Generosity within a society, just when people are more generous within a country, that people just tend to have a better attitude, I guess. They're very happy because they're making other people happy by being generous. Perceptions of corruption. It's basically just how much we trust the government. It's how much we think how much people think there's corruption in the government or businesses. We kind of just took the average of both the government and businesses. Crime index, just how much crime there is. If there's a high crime, probably a lot of people would be sad if they got robbed. Median income, basically just the average income. If you have a high average income, you're probably very happy because you can spend on stuff that you want. Extreme poverty rate, it's the people living under $2.15 a day. So basically just all the homeless people. And usually I think people would be sad if you were in extreme poverty. Literacy rate, if you have a higher literacy, um, I just feel like you'd be more confident in yourself. You'd be happy because you know how to read, you know how to write, you have confidence in your ability to do those things.
And this is our initial model. We found that the log GDP per capita and median income were both insignificant, which was surprising because at the beginning, we want to see how money affect happiness. And the significant variables are healthy life expectancy, social support, freedom to make life choices, and crime index. However, there are some variables that do not make sense. For example, the crime index and the adult literacy rate. Like both of them had coefficients that are like wrong. The adult literacy rate coefficients was negative, meaning literacy rate will have a negative effect on happiness. Crime rate coefficients was positive, meaning that more crime makes people happier. However, this result were both not very significant.
Slide. Now on to our descriptive statistics. I won't go over everything, but I'll point out a few that we found interesting. So firstly, the maximum for the ladder score was only 7.8, which I thought was perhaps a little bit low. And we're also surprised that the mean for healthy life expectancy was only 65, which is, I think, much lower than the healthy life expectancy for the US. And I also found surprising that the mean for the generosity score was negative, and that the variance for median income was very low. And then next, we decided to test for heteroscedasticity using White's test, and these were our results. Our p-value ended up being 0.529487, and because it is larger than our significance level of 0.05, we failed to reject the null hypothesis, and we can conclude that there's no evidence of heteroscedasticity.
Next we did a variance inflation factor test. So, well, basically we kind of thought there was a strong multicollinearity between our variables. So which is kind of a problem because it's considered problematic if both values are over 10. We can see that log GDP per capita and the Human Development Index are both over 10, and it may indicate a collinearity problem. It doesn't say that it's a collinear problem, it just indicates that it might be perfect multicollinearity. And it's kind of hard to interpret because a multicollinearity can make it hard to interpret because individual coefficients and separate effects due to its calculating every single thing all together rather than individual effects. Um, Log GDP and per capita and human development index actually kind of makes sense as to why their values are over 10. Because if you look at our variables, they're actually calculated by some of the variables already in our graph, such as the human development index is the quality of life. So it's measured via healthy life expectancy and adult literacy rate, which are already in our model.
And since we have variables with high variance inflation factors and variable with coefficient that did not make sense, for example, the crime index has a positive relationship with the ladder score, but it is supposed to be negative because theoretically, as crime index decrease, the ladder score should increase. However, in our model, it doesn't make sense. So we wanted to see if this variable actually had an effect on our dependent variables. So we decide to perform a what test. We are testing the joint effect of HDI, crime index, log GDP per capita, and adult literacy rate. So we set the coefficient into 0. The result is the p-value is 0.196259, which is greater than 0.05. So we failed to reject the null hypothesis that these four factors do not jointly contribute to our model. We can remove them in our new model. So after we remove that four variables, this is our final model. So we can see that the social support, freedom to make life choices, median income, and extreme poverty rate were all statistically significant at a 1% level. And generosity and perception of corruption were not statistically significant.
We also decided to test our model. So above is our equation, and for this example, we decided to use Pakistan, and their actual ladder score was 4.55. And after we plugged in the numbers into our equation, we found that our predicted ladder score would be 4.65, which is very close.
These are our references. Thank you. Any questions?
And there is still time for questions, so anyone who's online or anyone here who has any questions, please ask them. If you're online, you can either type something in chat or you could just unmute your mic.
Hi, this is Yamin
Okay,
Scardili.
nice work.
Oh, can you hear me?
Thank you.
All right. So my project's about the governance and climactic drivers of national water vulnerability, and it's an econometric analysis of the 2016 to 2022 averages. So I just wanted to preface this by saying that explain why should we study a nation's water vulnerability? Because water scarcity is a growing problem in many parts of the world, and without sufficient access to water, sanitation and hydration is becoming increasingly more difficult for a significant part of the population. And what I hope to achieve through this model is to identify what factors have the biggest effect in reducing a country's water vulnerability to help prevent a future water crisis potentially. And here are some statistics that 1 in 3 people globally do not have access to safe drinking water, and 4.5 billion people live without a safe toilet. So through my model, I hope to kind of help solve these problems. So I just want to explain my data first. So my data comes from the Food and Agricultural Association of the United Nations, the Climactic Research Unit, the World Data Indicators Data Finder, and NDGAIN, which was a research initiative done by Notre Dame University. It was like more focused on how countries are able to adapt to changing climates. And I wanted to analyze the data from 2016 to 2022, but I wanted to maintain the relative simplicity of the model. So what I did is I computed the average of all the data points over the interval and used the average data points in the model. There are 148 countries involved in the data set, and I used a linear regression model through ordinary least squares estimation to examine how governance and climate-related variables impact national water vulnerability. So there are two main things that impact national water vulnerability. There's basically government and climate. And the reason for these two factors is because government intervention and preparedness can help mitigate or even prevent a water crisis if done correctly. And climate conditions, specifically precipitation, can have a significant impact upon a country's water resources, therefore having an impact on the country's water vulnerability. So the variables I'll be using in this model are the average precipitation from 2016 to 2022, which is a climate variable. The RQ estimate is basically a regulatory quality score, and it basically reflects a government's ability to implement sound policies, to develop sustainable laws and regulations that help decrease a country's vulnerability score. That's also averaged from 2016 to 2022. Then you have the corruption control score, which also reflects a country's integrity in public institutions, which is also averaged. And then finally, the rain regulation quality. This is an interaction variable, which is basically the product of the precipitation average and the RQ estimate. And it shows how regulatory quality amplifies the effect of rainfall on water vulnerability. And the dependent variable for this is going to be the water vulnerability score by Notre Dame Global Adaptation Initiative, or like the NDGAIN, and it explains how vulnerable a country is to water scarcity. And basically, a higher score means you're more vulnerable. I just want to take a moment to explain how the vulnerability score is calculated, because there could be, I want to explain how the independent variables I'm using don't actually make up the vulnerability score, because vulnerability score is calculated through projected change in annual runoff, projected change in groundwater recharge, freshwater withdrawal rate, freshwater dependency ratio, water access and sanitation, and water infrastructure capacity. And basically all the independent variables I chose were not directly correlated to the factors that went into calculating the water vulnerability score. So there shouldn't be any like direct multicollinearity in the model. Here are some variable statistics. So the mean, median, standard deviation, the minimum and maximum of each variable. And these are the regression results. So after I ran the regression, I found that RQ estimate was significant at the 5% level, which is pretty strong evidence that it has an impact on water vulnerability. And it had a negative coefficient, which means as the RQ estimate increases or as the country creates more regulations, it's seen to have a impact in decreasing water vulnerability score. And the interaction variable had really strong significance at the 1% level with a positive coefficient, which I'll get into a little later. And precipitation recent average was not significant, and corruption estimate was also not significant. I did a heteroscedasticity test, or White's test, because the p-value is greater than 0.05 in this test. There's not enough evidence to reject the null hypothesis, which means we cannot sufficiently support the idea that the presence of heteroscedasticity is there, so therefore no correction is needed to the model. To interpret these results, basically regulatory quality alone, keeping all other variables constant, it had a significant negative effect on water vulnerability, which means even without rainfall, suggesting that strong governance alone plays a key role in reducing risk. And there's a quantitative effect of that. It's like a 1-point increase in the regulatory score can lead to a 5.45 percentage point decrease in water vulnerability score. Of course, holding all other variables constant. The interaction between rainfall and regulation was highly significant and positive, indicating that regulation is especially effective in low rainfall countries. In contrast, in high rainfall regions, additional regulation may have reduced impact or even increased vulnerability due to things such as inefficiencies or mismanagement. And the effect of that is like a 1 unit increase in regulation combined with a 100 millimeter increase in rainfall could lead to a 0.00343 point increase in water vulnerability. And like I mentioned before, rainfall alone was not significant, meaning that without effective governments, more precipitation does not necessarily reduce water vulnerability. Because if you think about it intuitively, right, a country has to have the resources to harvest that water, make use of it, and kind of turn it into something that people could use. And then corruption showed no clear effect. I don't think this is necessarily true. I think it's because if you think about how corruption happens in governments, corrupt governments don't continuously fail in their countries, right? It happens through irregular episodes, such as maybe scandals and stuff like that. So I think that's a little harder to capture over multi-year averages. So I think that is one limitation of this model. Here's some graphical representation of the regression results. This is the RQ estimate versus water vulnerability itself. So holding all other variables constant, as I said before, you can see how there's a trend where if the regulation increases, the water vulnerability is decreasing. And then this is a graphical representation of the RQ estimate times the precipitation recent average versus water vulnerability, or basically the interaction variable. And this is basically shows the kind of dual effect of the interaction variable. So basically with no rainfall and high regulation, there's the lowest water vulnerability. The red circle is like a reference point. I'm just going to rotate the same graph around to show you different points on the graph. So yeah, basically to interpret this graph, you can say that no rainfall and high regulation has the lowest water vulnerability. Relative to that, if we have high rainfall and high regulation, that's relatively higher water vulnerability. It's not the highest, but it's just relatively higher compared to the impact that regulation would have in, say, a drier country. And then finally, the highest point on the graph was pretty obvious. It was no rainfall and no regulation would have the highest water vulnerability. And yeah, that's the my model.
Okay. Either online or in person.
Yeah.
I understand your interaction term between the regulations and precipitation was significant.
Yeah.
Did you find that rainfall or precipitation average, did you look at a model where there wasn't an interaction term? Was it significant in that case?
I didn't necessarily look at a model without the interaction term. I felt it was necessary to just include it because I felt that it's very like I think if you look at precipitation alone, it kind of explains it in itself, right? Because I saw that precipitation wasn't significant, so that shows that without regulation, precipitation just doesn't matter. So that interaction term was kind of necessary to capture that regulatory effect on precipitation and a country's water vulnerability.
Thanks.
And nice work with that new plot.
Thank you.
Because that wasn't there when we looked at it.
Yeah, I added it last night.
Very nice.
Thank you.
Okay, the next group. And again, I'm sorry for the people who are presenting that we don't have the remote. It kind of got stolen last night.
That's right.
All right, so my project was predicting an NBA team's probability of making the playoffs. And so for this project, I collected data from all of the 30 NBA teams over the past 2 seasons to see which statistics were the most significant in a team making the playoffs. And so just for context, the top 8 out of the 15 teams from both the Eastern and Western Conference make these playoffs. Okay. So I used a probit model through least ordinary squares based on 60 team statistics, which explain their success in making the playoffs or their lack of success during the regular season, which led to them not making the playoffs. And I used 7 independent variables slash team statistics to determine a team's probability of making the playoffs. And so the model, the Probit model, explains the relationship between these team statistics and whether a team makes the playoffs, as well as the varying significance of each of these variables. Alright, so the independent variables. Okay, so using a likelihood test, all the independent variables included in the data set were deemed to have a significant effect on team's probability of making the playoffs. So there were actually a lot more independent variables that were than those that were included in the model, because many of them were deemed to not be significant enough to like be shown in the model. And so the ones that were included were conference, offensive rating, defensive rating, effective field goal percentage, turnover rate, pace of play, opponent effective field goal percentage, and opponent turnover rate. Okay, so these are the summary statistics. So these are the statistics from the total sample of all 30 NBA teams over the past 2 seasons. So something I found surprising from this chart is how the mean for offensive rating is lower than the mean for defensive rating, while the median for offensive rating was actually higher than that of defensive rating. And the reason I came up for this is because the mean would be lowered substantially by the teams at the bottom of the conference, which might be tanking, which would therefore like lower the mean a lot relative to like if you just took the middle sample and the teams in the middle, they would definitely be performing a lot better than the median of the better teams and the median of the terrible teams. Okay. Yeah. Okay, so this was the resulting model, and like it says like on the bottom, if the p-value is less than 0.05, it is deemed to be like very significant, and it's marginally significant at 0.1. And so the further the z-value from 0 also equals higher significance. Okay, so by like studying this, I saw that the two most statistically important variables were offensive and defensive rating, which makes sense because they're just like an overall measure of all the other independent variables. So I'd like also looked at the other independent variables to see which ones were most important in leading to a significant offensive and defensive rating. And so by looking at that, I found that the most significant were effective field goal percentage and possessions of per game, which is basically just their pace of play. So how many shots and possessions they can get just from playing faster, as well as the opponent turnover rate. Okay, so by observing the p-value for offensive rating, which is lower than that of defensive rating, and observing that there are more statistically significant offensive variables, it can be determined that a team's offensive rating is the most important factor in a team making the playoffs. Okay. So these are the limitations of the model. So the first limitation is injuries, and because so the model didn't account for injuries because it's a random like independent variable, which is like impossible to measure like through the Probit model I did, because we can't just like account for things that like are random and like could happen at like any time and aren't based on any sort of statistical like measures. As well as another limitation would be mid-season acquisitions. So if a team were to perform very well at the start of the season and then trade their best player, then they would definitely be a worse team, but the model wouldn't be able to like accommodate for that. So it would be impossible to predict that drop off in the overall statistics. Okay. So the model concluded. Okay, so for this project, I studied the effects of varying statistics on NBA teams' probability of making the playoffs. So the objective of this was to be able to determine what made NBA playoff teams successful during the regular season and what led to other teams not making the playoffs. So the resulting model proved offensive rating, including the other independent statistics which would lead to a high offensive rating, to be the most crucial to NBA teams in order to secure a high seed and make the playoffs. Yeah. Yes.
Would you mind describing for everyone how the offensive rating or defensive rating are calculated?
Oh, yeah. It's actually pretty simple. It's just the points per game. So it's just offensive rating is just the points they score per game, and defensive rating is just the points they allow per game.
A follow-up question, could you answer the model, John?
Yes.
So one thing I was noticing is the defensive ratings coefficient is a little, while it's most significant offensive and defensive, it looks like defensive has a larger effect. And I was wondering if you noticed the same thing. I know it's less significant, but
Yeah, I mean.
would you say defense wins championships, or do you not have enough?
I mean, I mean, yes, like, I mean, yeah, defense wins championships at like a certain point, but not necessarily like during the regular season. So in order to like secure a high seed, I think offense is more important, but to like make it through all the way, I'd definitely say that, yeah, defense wins championship.
Good answer.
And just a couple of clarifications. You mentioned that this was an OLS or Probit model. It was actually a maximum likelihood model that you used. It wasn't.
Oh, wasn't it?
And the other thing you mentioned that it wasn't possible to capture the effect of injuries. That actually could be captured if you had data on that, because that could be included in the outcomes there, I think.
Oh, I just meant like within like the model, like I used.
Right, but if you modified the model.
Yeah, no,
it-
yeah,
it
sorry,
could
no, that's-
capture them.
yeah,
Okay,
okay.
very good. Any other questions from anyone in person or online? Okay, very good. Thank you.
Okay, so our presentation was on demographic determinants of music preferences. To start off, our model's goal was to determine to what degree different demographic determinants such as income, race, sex, and level of education affected music preference. To do so, we utilized the GSS survey, or the General Social Survey, which is a nationally representative survey of adults in the United States that has been conducted since 1972 by NORC at the University of Chicago. While the survey's questions and data varies from year to year, for our project, we specifically utilized the GSS survey from the year 1993 in order to gather data and observe how music preference could be connected to a person's background and overall demographic. And these are the variables that we utilized.
So our dependent variable was obviously music preference. And for our first independent variable, we used age. So this just included the respondent's age at the time of taking the survey. The ages ranged from 18 to over the age of 89. And we thought this variable was important because it allowed us to measure the progression of social dislikes and social norm changes over multiple generations. The next variable we used was the level of education the respondent had. So these took into account things like less than a high school degree, associate, junior college, graduate, or a bachelor's degree. And by measuring the level of education, we could receive a better indication of how higher level of education affects music preferences.
We also utilized the variables income and sex. So income was measured between $1,000 and $75,000 annually per household. But some people either didn't answer or put in applicable. So this is just like one restriction on our model. We believed that this was important because measuring household income allows us into a closer look at socioeconomic class of each individual responding. And we also measured sex, so both female, male, and those who chose not to respond, which allowed us to determine if male and females have different preferences, and if so, how they differed.
The next variable we used was area, where the respondent was located. So this measured the location where the survey was taken or where the resident resides. So we included Western, Central, and Atlantic area. And this just allowed us to see that if different areas of the United States have stronger music preferences for different music types.
We also measured employment, so whether or not the respondent was employed, unemployed, and other circumstances. And this allowed us to see the status and work and lifestyle had any effects on favoring a specific type of music.
Okay, so for our important variables, the reason that we determined our 6 variables of age, education, income, sex, area, and employment is because we deem them to be some of the best things that can be both determinants or indicators of someone's life and how that can represent their taste in music. We think that it's important to explain someone's economic and general background. It's also one other topic of note is this survey was taken in 1993. So the 1,000 to 75,000 household income range might seem low now, but that was back then. And the 4 types of music that we chose to do were classical, rap, oldies, and heavy metal.
So for our descriptive statistics and our results, we first focused on classical music.
To give a brief explanation for each of the 4 columns, the coefficient represents the relationship between the dependent variable and each independent variable listed. So the higher higher it is, that means there's more strong of a relationship, and positive or negative means if it's a positive or negative relationship. And then the p-value, the far value on the right, represents how much statistical significance can be measured from the relationship. So what it would mean is if it's 3 stars, that would mean it's significant at a 1% significance level, which means there's only a 1% chance we can say that there's no relationship between our values. So when we look at the data we got for classical music, we saw that both there was a strong positive relationship between having a bachelor's degree and having a graduate degree in liking classical music. And likewise, there was a strong negative relationship between having less than a high school degree and disliking classical music. Also of note was there was a negative relationship between being male and liking classical music. And I guess this can kind of tie back into the level of education, but also the log income had a positive relationship with liking classical music. And then to look at some of the descriptive statistics for classical music for this model, there's our mean, variance, minimum, maximum, which kind of tell us the average and the spread and the range among our data. So our mean was a 2.33, which means on a scale of 0, meaning strongly dislike, to 4, being strongly like the average person, it's been at a 2.33. The average answer was about 1.47 places away from the mean, and our minimum maximum are the lowest and highest choices.
We also looked at rap music, and we found that there was a negative correlation between having a graduate degree and liking rap music, which is significant at a 5% significance level. However, there was a strong positive correlation between being employed and liking rap music, which is significant at a 1% significance level. And we also observed some other things within the data, but we can go into greater detail if need be. For our descriptive statistics for rap, we found that the mean was 1.08, the variance was 1.25, and then minimum and maximum both being 0.0 at both ends of the scale.
As for oldies, which is kind of defined as a period of music from like the 50s to the 70s, we found that there was a negative relationship between having a graduate degree and liking oldies music. And there was also a negative relationship between having less than a high school degree and liking oldies music, which we found interesting. As for age, we found that there was significant at a 5%. There was a positive relationship between linear age at a 5% significance level, but there was a negative relationship between square age and liking oldies music at a 1% significance level, which indicated to us that the relationship between liking age and liking oldies music wasn't linear, but it was quadratic. And yes, We also noticed that there was a strong positive relationship between being employed and liking oldies at a 1% significance level. And then as for our descriptive statistics, our mean value was a 2.75, which is particularly high, we found. Our variance was a 1.23, and then our minimum and maximum were the two ends of the scale.
So the last music we covered was heavy metal music, and by running this model, we found that there's a strong positive correlation between being male and liking heavy metal music, and this was significant at a 1% significance level. There's also a strong positive correlation between being employed and liking heavy music metal, which was also significant at that 1% significance level. However, there's a negative correlation between a higher log of income and liking heavy metal music, which was significant at a 1% significance level. So this means that these two are negatively correlated, which we like we'll get into that later.
Yeah, with our expectations versus results.
And so, like already said, the mean was just the average answer to this question. So 0.88, and then the variance was 1.22, and the scale was still from a 0 to 4. So, our expectations versus our results that we got were our expectations for classical music. We figured that it would probably be liked by higher income, older people and with a higher education who were employed. But we found out.
We found that it was more likely to be enjoyed by those of higher education, which correlates with our expectation. But it was more popular in the Western area, those of higher income, females, and older people. So it shocked us a little bit specifically on area. We weren't really sure where it would be most popular, but the other things we were able to predict pretty closely.
The next expectation was for rap, and we figured that this would maybe be more liked by lower income, younger people, and mostly males.
And that's essentially what we found. While there was no difference between female and male preference, we did find that it was liked by those who had received lower education, who had lower income, and were employed.
And for the oldies category, we figured it was mostly going to be liked by more middle-aged people, since at the time of this survey, they probably grew up on that sort of music. And we figured that they would probably be employed as well.
And we found that it was most enjoyed by those of average education, not central area, because there was a negative correlation on that model, and they were employed.
And lastly, for heavy metal, we figured that it would probably be liked by males more in the Western area on the West Coast, and we thought it would be liked by younger people.
So partially this was true. It was favored by males, but they were lower income and employed.
Alternative results. While our project itself could have the results and outcomes altered by utilizing different variables, there are no real proxy models that could reverse the way we observe this project. Essentially, while our project confirms that specific demographic determinants can affect our music taste, it cannot be measured to determine whether music types can affect a person's demographics, as most of these things can't be altered, which does make sense. Liking a specific kind of music can't change your age. In addition, we cannot perform tests such as the wall test or tests to measure heteroscedasticity due to the way our data was displayed, which was on a number scale, like from zeros and ones and zeros to fours. So we couldn't really look for tests with that.
We had to make dummy variables for all our variables because all our data was collected in words, which we couldn't insert into our model program. So that was a reason why we couldn't run those tests as well.
So our results. After conducting multiple regression models on our data, we believe that the demographic determinants that were most prevalent and having an effect on all music types were education, age, and income. However, area, with a few exceptions, gender, and other variables we ultimately omitted, did not hold any major indications on preference for music. So while these were most important, all of our variables did play a role, just some to a greater degree than others. Thank you.
Yeah.
So any questions from either people in the room or online? And if you're online, just
Hello, can you hear me?
wait, we may have an issue with the sound.
Hello, testing.
Oh. You make sure it's going to the right output. Jordan.
Hello?
Yes, we can hear you.
My question is, what are the limitations of your model? And what were the results of your wall test?
Although we didn't have a wall test due to, like I said, we had to use dummy variables, so we couldn't perform this test.
Well, you could actually do a likelihood ratio test, and that was on the output, and they were all significant.
Yeah, and then to answer the first part of the question, I guess the restrictions of our model. Like we mentioned before, due to some respondents not fully answering questions on income, either leaving them blank or inapplicable, that definitely played a role in restricting what data we could receive. And in addition, a lot of the options on the survey are not really relevant today, if you will. So some of them kind of were time specific. So based off of the 1993 survey, the questions no longer really made a lot of sense. So that kind of controlled which variables we could and couldn't use and how they affected our model. So we originally started, I think, with close to 13 variables, and we ultimately omitted a lot of them that were restricting our ability to like correctly and accurately predict the data.
For example, we had a happiness level scale, but we found out that this wasn't extremely significant in our model.
Another limitation.
Thank you.
Another limitation, I believe, was while other projects were working with much smaller degrees of freedom, like maybe somewhere from 50 to 100, ours was over 1600, which meant that there was a lot more data to be analyzed. So we couldn't work with as many variables for our project.
Thank you for the question, Ed. Is there anything else?
We have another question. We have a question for Connor. What were
Are you guys at the airport, by the way?
the variants of your regressive?
What was the variance for our regressive model?
Well, we had multiple.
We had multiple regression models,
We had to measure 4 different dependent variables.
and
but
they're all written
I
in the
can
presentation.
read out our variances to you right now. For classical, it was 1.47. For rap, it was 1.25. For oldies, it was 1.23. And for heavy metal, it was 1.22.
One thing you didn't mention, why did you use 1993?
Because
This was the
Well, you mentioned that year, but did you mention the reason?
This was
Yes.
the only data we found on the general social survey that would analyze all these different types of music preferences and all these other variables. So this was kind of the only year that we found accurate and like concise data for.
Because they have different questions every year. Some questions are standard and others are different topics, and that was the only year that they had the music preference question.
Are there any more questions on Zoom? Oh.
And how many people are there on Zoom in this account? Is it just Jackson?
Oh, I thought that was Edward.
Oh, is it Edward?
Yeah, we were hoping Jackson would tune online.
Okay.
Did you have a question, Ben?
Yeah. Obviously, I thought it was interesting that being employed positively correlated with the heavy metal and the rap, while as your income goes up, that wasn't going to help. So the lower income but employed people liked heavy metal and rap. I'm curious if you were able to find something based on ethnicity that seems relevant, perhaps. In
Yeah.
1993 at least.
So ethnicity was one of the variables that we utilized at first. It ended up really not playing a role in, I think, any of our models except for rap. And we ultimately did have to get rid of it because we were having to create a dummy variable for every single ethnicity, which obviously takes a very long time. So when we saw that it really didn't add to our data, we ultimately omitted it.
Thanks.
Okay, any other questions? Again, either from the room or online. Okay, very good, thank you.
And what type of model did you guys use? Like a time series?
What was that?
What type of model did you guys use?
Panel.
Time series.
We had a section for these questions, Edward, but ask what model we use. We use it. We use it.
Sorry, can you come back to the camera, please? I didn't hear that.
Okay.
We used an ordered probit.
No, you're not in the camera.
Okay, you can bring more questions in later, but we're gonna get to the next presentation. And you could have presented from there, wherever you are. You could have done this remotely instead of yesterday.
All right, so my model or my project is the impact of alcohol, marijuana, and nicotine usage among 12 to 17-year-olds on the expected years of education by state. To explain my model, I obviously had alcohol, nicotine, and marijuana usage amongst teens aged to 12, 17 as the dependent variables, and as the independent variables, and the dependent variable was expected years of education. I used a linear regression model, and I also included other control variables like median household income, student-teacher ratio, unemployment rate, and urban population percentage, because these would account for most of the variation in expected years of education. So then I could more directly see the actual influence of the substances and not like other things. And that doesn't mean these variables aren't equally as important. They're obviously equally as important, but that's just not what like the main point of my model was. And is that my model? Yeah, that's my model. Expected years of education is the Y, and then I have the constant and all the coefficients and all the variables. This is what each variable actually represents. So it's like percentage of kids 12 to 17 are reported, the different substance uses, as well as median household income, unemployment rate, student-teacher ratio, and percentage of urban population, like I said. And then that's a linear regression model. And these are the descriptive statistics. So this is like the mean of all those variables, the maximum, the minimum, and the variance. The variance for median income looks really high. That's because you got to like square it. And since this number's in thousands, if you square it, it gets really big. And that's why also for some of these, it's really low because it's in decimals. So if you square it, it gets really small. Yeah, these are the results of my model. So first thing I want to look at is the p-values. What this model shows is that marijuana usage per month, or marijuana usage and nicotine usage, are not significant at all. Their p-values are very high, which basically means there isn't really evidence that these numbers matter. And urban population is significant at the 10% level, which means it's significant but not very. And then at a 5% level, alcohol usage per month, unemployment rate, and student-teacher ratio are all significant at a 5% level, and significant at a 1% level is median income. And the T ratios also show basically the same thing. It's how significantly different these coefficients are from zero. And so the lower it is, the less significant the coefficient is. And as you can see, the lowest numbers are for nicotine and marijuana, exactly the same as the p-values show. The coefficients represent the actual effects of each of these variables. So the constant being 15.3, basically that means that no matter what, you're going to have 15.3 expected years of education, no matter like what state you're in. And this doesn't depend on the variables. These numbers look kind of big for alcohol and marijuana, but since I put it in as percentages, a 1% increase would actually only correspond to a 0.05 year increase for alcohol. As you can see, this number 5 here. And median income, if you increase your median income in the state by $1, you're going to increase your expected years of education by 2.3 times 10 to the negative fifth. Or if you increase it by $100,000, you're going to get a 2.3 year increase. Unemployment rate and student-teacher ratio and urban population percentage were negatively correlated with expected years of education. So as these go up, expected years of education should go down, which makes sense, but not really for urban population. But since that's significant only at a 10% level, that doesn't really matter that much. And then if you look at the numbers under, the standard error of regression and the sum of squared residuals basically show the same thing. But basically what that means is that on average, my model's predictions of the expected years of education are off by 0.17 years, which is, I think, is pretty good personally. The R-squared value of 0.825 means that my model explains 82.5% of the variation in expected years of education. And a large F statistic of 28.36 shows that the independent variables are actually what's impacting that, and it's not just by random chance that that's happening. The next test I ran was a variance inflation factors test, which is to make sure there was no multicollinearity, because I suspected that people that use alcohol or marijuana or nicotine are more likely to use other substances. So I wanted to make sure that these variables weren't dependent on each other and it wouldn't ruin my model. But as you can see at the top, all the values are below 10, and values above 10 may indicate a collinearity problem. So my model was fine. Next, I tested for variable emission. Since the p-values on marijuana usage and nicotine usage were very high, I decided that they probably wouldn't matter in my model and they were probably hurting it more than they were helping it. So I tested for variable emission. And as you can see, the null hypothesis is that the parameters are 0. And a p-value of 0.62 means that I can't reject that. So you can't say the values are not 0, which basically means that the variables don't matter because the coefficient on them might be 0 and it might have absolutely no effect. So because of that, I ran a new model without these two variables, and not a lot changed. The only thing that really changed, some of the coefficients shifted a little bit, but not by that much. Alcohol usage is now significant at a 1% level, so it's now more significant. And the F statistic changed. That's really the only other statistic that changed. It went up, which basically means that now my independent variables are more directly affecting expected years of education since I got rid of some variables that didn't really matter. The next test, I don't know how to pronounce this, but it's like the Broish-Pagan test or something. That's for homoscedasticity. And the null hypothesis here is that there is no heteroscedasticity. And p-value of 0.19 means I can't, it's like triple negative. So basically there's no heteroscedasticity and there is homoscedasticity, which means my model's predictions are pretty accurate. And my conclusions, I already talked about a lot of these, but marijuana and nicotine usage don't really impact the expected years of education in a state since their coefficients were insignificant. And alcohol consumption actually very slightly improved a student's years of education, expected years of education by about 0.05 for every 1% increase, which was supported by a strong p-value. I don't really know how to explain this, but I decided that the only way to that makes sense is if alcohol usage and median income are correlated. A state with more income or a higher median income might have more alcohol flowing through it. So that could explain that. And median income was also significant at a 1% level. And student-teacher ratio and unemployment rate were both inversely related at a 5% level. And the percentage of population that live in urban areas was inversely rated at a 10% level, which was a bit of a surprising result because that basically means that the more people that live in cities, the expected years of education go down. But at a 10% level, like you really never know. So, yeah, that's really it. Thank you.
Just to clarify a few things, you were dealing with statewide data, so you're looking at what characteristics of the state population affected median educational.
Exactly.
And you said that the average would be 15 point something years of schooling. But I think that should be noted that that's only if all those other coefficients are 0. So if there was no unemployment, if there was no urban population and all those other factors were 0, that would be the level, right?
Yeah,
But in general, are there any states with 0 unemployment?
No.
So we would actually expect the level of median to be a bit lower, the average to be lower, right?
Yeah.
Any other questions from either anyone in the room or online?
Yeah, what's up?
I was wondering if, since we're not really just talking about teenagers, but 12 to 17-year-olds, and it's very interesting that the alcohol coefficient is positive with years of income, with years of education. Do you think maybe that helps people get past their freshman year of college or something, just being introduced to alcohol earlier? Or what conclusion are you willing to make?
There's a chance, obviously, I'm not ruling anything out, but I thought that it would more rely on like household income. I thought that maybe adults with higher income and more alcohol in their house would be more willing to let their kids try some, or they might be more familiar with it and they would use it more. That was really what I thought, but that's also possible.
And there might be regional differences since you didn't control for region.
Oh yeah, yeah.
Because there are differences in alcohol laws across states and so on. It may be correlated with that. Okay, any other questions? Okay, very good.
Thank you.
It's not like you. What's going on? Everyone's so concise.
Okay.
So now you've got almost an hour.
So should I do for an hour? Okay, so here's my presentation. Before the presentation starts, I want to notify two things. So at first, please forgive me for any mispronunciation or incorrect grammar used in the presentation. And secondly, I choose this topic simply because I encountered theft crime in Washington D.C. before when I went for a trip. So it's a very traumatizing memory. So I just decided to use this as my topic. So here's the topic: drivers of the theft crime, time series analysis of Washington D.C. monthly. Here's the table of contents. This is the step I followed to get a conclusion of my research. So at first, I established a hypothesis and collecting data from it. Secondly, I used the data I collected to define variables, and then I use variables to establish the model and analyze it. And lastly, I make the conclusion based on what I discover on the model. So let's start with hypotheses and collecting data. At first, my hypothesis is that I established that variables including unemployment rate, precipitation, etc. in Washington, D.C. from 2014 to 2024 will be significant factors that determine the number of theft crime happened in Washington, D.C. And here's the data I use. Because the main question I want to talk about is how unemployment rate and theft crime related. So these two will be my main variables. And to make the model more accurate, I also have extra variables, including TVAG, represent for average temperature, precipitation, and average salary. The website I use to make these data accurate, or BOS, stand for Bureau of Labor Statistic, Open Data DC, and NOAA. So now let's define variables. Based on the truth that the whole presentation is all talking about how all the variables affected on theft crime. So definitely theft crime rates will be our dependent variable, and unemployment rate, TVAG, precipitation, and average salary will be my independent variables. Also, to make the model more accurate and to avoid dummy variable trap, I use May as the base mouse, and which can avoid the perfect multicollinearity, which means variables exactly represent by a linear combination of others, which cause the model to fail to estimate properly. And here's my descriptive statics. I have mean, maximum, and minimum for every variables. And now let's establish my model and analyze it. At first, I use the traditional ordinary least square technique, and this is the table I got for the first time. So we can notice that in the red square right there, precipitation and average salary will be pretty significant factors that affected on the crime rate in Washington, D.C. from 2015 to 2024. And we can also find out that unemployment rate, what I mainly discover on, is actually not such a significant factor related to theft crime rate. But that's not it, because the model used time-based data. So what happens in one month may affect it on the next month. So which means the autocorrelation is essential. And because ignoring it, it can make the result appear more certain than they actually are. And the way I use to check if autocorrelation is essential is by the Durbin-Watson value. So once the Durbin-Watson value, which is in the red square, if it have a huge difference compared to 2, it represents that the model does affect by autocorrelation a lot, and we need to consider that as the situation. So this graph on the left is my first model, which does not consider the autocorrelation. We can find out that the value is about 0.66, which is a huge difference compared to 2. So that's why I decide to reestablish the model and considering the autocorrelation. We can find out the value turned to 2.19, which is way closer to 2. So make the table more accurate. And the way I use to re-establish the model is to use GLS, which represents generalized least square technique, which provide more efficient and reliable coefficient estimates. But we can also find out that after we create this model, the p-value on the right side of the model, they are like significantly big compared to what we originally discovered. So what that means is data were more precise and reliable, but also provide the truth that none of the variable I choose could significantly affect on theft crime rates in Washington, D.C. And now, last but not least, we're going to conclusion. So after the research model created depend on data could prove that my hypotheses of unemployment rate, precipitation, average salary, and TVAG in Washington, D.C. from 2015 to 2024 was significantly affected on theft crime rates at that time period does not hold. And now I want to kind of discuss why this could happen and what's the reason variables does not significantly affect on the crime rate. So first, I think it's because of the shortage of the time range. So although I did have 108 observations for each variables, but all of them were recorded in monthly changed, which may not fully record significant variation. Secondly, effects may require a longer time to show influences on crime rates, such as annually or seasonally. And second is probably because of the lacking of important variables. So while I'm searching for data, I might neglect it or unable to find data from DC that might be very important for the research and cause significantly effects. As a result, the variables in the research right now were mostly insignificant. And thank you so much for your kindness and patience, and here are my sources.
Okay. We'll stop the recording. And the recording, by the way, will be posted. If I have enough time, depends on how much time to give me to get out of here. I will post it before I leave here. Otherwise, it'll be posted tonight once I stop it overnight. And we stop the recording. Okay, now you have